Hello again, folks, in 113. Today we're going to be covering the solutions to test number 2, which should consist of chapter 2 and part of 5. You know what? I actually left my paper, so let me go upstairs and get that. I'm sorry. And then we'll go through it. Jumping the gun here. I'm not prepared. Anyhow, this is what test number 2 looks like. It is available to you as a PDF through my last message in in Canvas. It's 20 questions. They're not multiple choice this time, because they're kind of intricate. So anyhow, you don't have to submit anything for this. I just wanted you to have it more or less to gauge where you should be. All right. And really focus on your MyLab assignments, okay? Some of these are taken from MyLab, okay? So we'll go through this now. Let me adjust the lights and the camera. I have to change those batteries. Make it a bit dimmer in here. That's about right. Okay. So I'll go through these 20 problems to remind you, okay? What you should know to this point. And so far as chapter 2 and part of 5 are concerned. Okay. I think that is as bright as it's going to get. So let's continue. Alright. As long as it's legible, that's fine. Alright. Now this, maybe I'll zoom in just a wee bit here. It might be better. Alright. I tried to label it so that you know where to look for these types of questions. Alright, the first thing is to translate something from what is set builder notation into raster form. Raster form is a little bit more satisfying because you see the actual elements. Right, so this is an exercise in how well you could translate this more or less into English. This is basically, if you were going to read it out loud, the set known as A, and then the equal sign would be is. The set of all x's, and then this line would be such that, and then you would read the conditions that follow it, right? Remember, a lunated epsilon, which is the stylized way that this is written, says that x is an element of n, the natural numbers. X is an element of the natural numbers. And simultaneously, x is more or less between 2 and 8, but notice that in the case of its relationship to 2, there is an equals. So you might, to summarize, say x is between 2 and 8, 2 inclusive. I'm taking a little artistic license here in how I phrase this, but just for the sake of conciseness. All right. Now, remember, what are the natural numbers? The natural numbers are numbers that are intuitive to you as a person, right? Because we are taught to, when we're little kids, right, before we go to school, more or less to count on our hands, right? And we don't count 0, even though you could make that shape, obviously. All right, we go 1, 2, 3, 4, 5, and so forth. All right. No decimals, no fractions, just the regular whole numbers that are all of the positives. So if you analyze the natural numbers, elements of natural numbers would be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and it goes on infinitely. Right? But starting at 1, not including 0. Right? If you are going to meet both of these conditions simultaneously, that is to say that x is something between whole number 2 and whole number 8, then where you should be looking is basically from here to here, right? And then recognize the inequality symbol. This is less than or equal to, which means yes, 2 is definitely included, all right? But x is less than 8, all right? And there's no equal sign, so you're not going to include that. This is very subtle, but the word "and" is purposely written in this problem, which makes this an intersection. And if it is an intersection, which is normally abbreviated by that sort of horseshoe shape, that means that we're only interested in the overlap of these two conditions. Right? So all of the natural numbers would be starting from 1 going into infinity, but the overlap would begin here at 2. And so we're going to include 2, 3, 4, 5, 6, and 7, and then come to a screeching halt because it's just the overlap, right? And 8 is not included. Right? So the answer to this problem would be in raster form that A is equal to 2, 3, 4, 5, 6, and 7, and you should put commas in between them. I sometimes neglect to do that just because I think it makes it a little bit harder to see, at least in my crummy handwriting. Okay. Now, if you look at number 2, it says determine the number of subsets and proper subsets of the following. Use formulas and/or write out the possible combinations. You don't have to do that. That would be tedious, but it would, if you had no formula, it would help you determine the total number. The formula for subsets in general, which remember includes the very thing itself, would be 2 to the n. And n is the number of elements in the set, which in this case would be 3, right? The cardinal number is the number of numbers or the number of elements, right? Proper subsets would be things that don't look like the original thing. So that would be this formula, 2n minus 1. Right? If you recognize the cardinal number n as being 3, because it's x, y, z, right? And you substitute that here and here, then you know that number of subsets in general is 8. Right? But the number of proper subsets would be 7. Okay, so those are your two answers. Okay. Now, if you look at number 3, tenacious blue. Number 3 is the question of what is equal or equivalent. All right. By default, all right. Things that are truly equal are also equivalent, but not the other way. Equivalent simply means that they have the same number of elements. Okay? Equal means that they are exactly the same. So both conditions that they are the same number of elements and the same elements themselves. Exactly. They don't have to be in the same order though. So for example, if you had another choice here of C, and you saw it as 2, 3, 1, right? A and C would be equal, right? But in this case, we don't have that. We have A is 1, 2, 3 numbers, and then set B is countries, right? Brazil, England, Japan. Now, if you analyze these, the cardinal number of B is 3, and the cardinal number of A is similarly 3. Right? So that would make them at least equivalent. If you analyze what the elements actually are, however, that these are numbers and these are words, right, at the very minimum, countries specifically, then you would have to rule out equality. What you would simply say is that they're equivalent. Okay? All right, now if you look at 4, this is an exercise in how well you could read this. A, sort of upside down horseshoe, you know, B, right, is, remember the abbreviation for intersection, right? A, upside down U, B is A intersect B, which means that we're concerned with the overlap in the diagram. What is overlapping in the diagram would be this region here, which would normally be in Roman numeral 1, 2, 3, that would be region 2 specifically. So given the Venn diagram above, what is the actual intersection of A intersect B? It would be BDH. Okay? And we would use the same diagram for subsequent questions. So if you look at 5, it asks you for other operations. If you feel a little sketchy, remember there is a diagram I had made a while ago. I'll show it to you really quickly. These are some operations you would see and some idea of how to go about doing them. In summary, there's intersections which will be recognized by that symbol, and then there's a union, a complement, a difference, and a cross product. Right? Now what you see immediately in this other question is we're asking for, the royal we, the difference, right? So you would have to take into consideration what are the elements of A, and then subtract the elements of B from them. All right. Here's the strategy again. What would you do if you had to find a difference per se? All right. You keep only from A what isn't simultaneously in B. You're subtracting out what is in B, the things that are in common. In other words, cross out the matches. All right, if you have them listed in roster form, and then circle the leftovers in A, and that's what you're going to keep. Okay, so where's our diagram again? All right, we'll figure out what is all of the contents here. Sorry, it's not on the same page. The elements of A are everything encompassed by this red circle. So F, E, G, B, D, H. And the things that are in B are everything that are encapsulated by this blue circle. So B, D, H, A, I. All right. Again, as a strategy for dealing with this, cross out the things that match. So the overlapping area, the intersect, B, D, H. All right. And then just keep the things that are in A specifically. So the difference, to answer this question, would be FEG. Okay? Or EFG if you put it alphabetically, right? Right. Given the same Venn diagram, what is the complement of B? Remember, the complement of B is things that are not B, which does not just mean the portion of the circle that is A only, or the portion of the Venn diagram that is A only, but even the things that are outside of it. Right, so if you look at this diagram again, here are the things that are B, somehow or other. All of that would be B. What would be not B would be F, E, G, Q, R, S. So the complement of B would be, if I put it in alphabetical order, E, F, G, Q, R, S. okay? And then one more of these, the cross product. You don't need a diagram for this. All right. The cross product is more or less like pairing elements together to form what would be coordinates if we were talking about numbers strictly. All right. So as a strategy, what you do is you start with A, because that's the thing that's written in the front here. All right. And there's no commutative property for cross products. All right. The order definitely matters. And just draw connecting arrows to each element in the second thing, which in this case is labeled B, right? And then write them together as if they were an ordered pair. So for orange, you're gonna go, okay, orange 1, silly as that may sound, right? And then orange 2. Imagine your x-axis was orange, more or less. Right. Then a similar thing would be draw connecting arrows from banana to 1 and then to 2. So you have banana, 1, and then banana 2. Which again sounds like nonsense, it's just a strategy. And then apple 1, apple 2. Nice computers. Right. Apple 1, apple 2. Commas where they're appropriate and parentheses. Now, if this is in set notation, there should be a fancy braces like so to encapsulate everything. And technically, commas in between each of these. Okay, for listing. Okay. Here again is that overview, all right, if you're looking for some strategy to this. All right, as I mentioned, draw arrows connecting A's to B's. All right, if that is the order in which this is written in the problem, A written in front, then that's the way you do it. All right, if you had B written in front, then you would connect arrows from B to A and things would be backwards. Okay, there is no commutative property here. All right, let me get rid of that. All right, now to begin here, this is a 3-step Venn diagram which needs to be filled in before you can answer any question about the problem. So there's a strategy to that which is useful to learn regardless of the specifics of the word problem. Let me walk you through that again. Okay. The Roman numerals, again, are not elements, they're just regions. Okay. So, things that are in this sort of marshmallow moon shape here are region 1. Things in this sort of Star Trek symbol here, that's region 2, 3, 5 is this Roylo triangle, and 4 and 6 and 7 and outside is 8. All right. Of 500 people, 270 listen to hip-hop music, 320 listen to rock, and 160 listen to country music, right? 140 listen to both hip-hop and rock. 120 listen to both rock and country. 80 listen to both country and hip-hop. 50 listen to all 3 genres of music. As a strategy, what you should do when you're filling this in is start with the dead center. So, in the order that you would be encouraged to do it is figure out what should be in 5, then do 2, 4, and 6. Those are interchangeable. You know, I mean, in terms of order, you could do 4 technically first, but you might as well start with 2. All right. And then do 1, 3, and 7. And you do what is outside 8 last. And that's the strategy. Okay, how do you get from here to there? Well, ironically, start perhaps with the last sentence here. 50 listen to all 3 genres of music. this Roylow triangle in the dead center, this sort of shield shape, right, is the overlap of not just two things, but all three things. So that is where you would park a 50. Right. Now, if again you're sticking with this to do 2, all right, just realize what it is involving. It's A and B and C. I should probably label these. A we'll call hip hop. All right. B we'll call rock, as in bedrock. And C would be the one thing that is maybe intuitive, country, right? Because it's C. So things that are both hip hop and rock is this second sentence in the paragraph. All right, 140 people. So just pay attention to this much for the moment. All right. Now, if it's 140 in here, and we know a portion of that 140 is already dedicated to 50, this is really 140 minus 50, which would be 90 logically, right? So you would put a 90 in there, right? And you have 2 covered. If you now shift to region 4, which is over here, this pedal, if you will, all right, that's the next thing. 120 listen to both rock and country, right? Well, actually, that would be this one in particular, so I might as well start with that. This biscuit shape, all right? If it's 120 combined, and you know a portion of it is 50, 120 minus 50 would be 70, which means that in here, the overlap between rock and country is 70. Then, lastly, 80 listen to both country and hip hop, which would be this biscuit. It's 80 total, and you know a chunk of it is 50. So what's the difference? Well, it would be 80 minus 50, which would be logically 30, right? So you'd put a 30 here. Okay. Now to go to the regions beyond 1, 2, and 7 specifically, all right, you need to go back to actually the first sentence, all right, which is this here, all right. 270 listen to hip hop in general, but just realize that 3 portions of that we've already figured out, all right. So you'd have to figure out the sum of 90, 50, and 30 first, and then subtract it from the total of 270. So this is 270 minus 90 and 50 is 140. 140 plus 30 is really 170. The difference of 270 and 170 is 100. All right. If you did the next thing, which is 320 listen to rock, again, we have 3 portions of that already concluded, but if we figure out now the sum of these 3 parts and then subtract it from the total of 320, that would be 320 minus what? 140 plus 70 is 210, right? And the difference of 320 and 210 is 110. So you'd have a balance of 110 here. And then lastly, 160 listen to country, all right? All right, the whole kit and caboodle that is encapsulated by green would be 160, and again, we need to figure out this sum first. So this would be 160 minus the total of 30, 50, and 70. So 50 and 70 is 120, 120 plus 30 is 150. The difference of 160 and 150 is 10. So this would just be a 10 here in this balance. Right. And then there is lastly the region that is outside all 3 parts of the Mickey Mouse head, if you will. All right. Or dead mouse, is that it? Kind of looks like that helmet, right? 500 is the total number of people, right? We would have to figure out the sum in theory, of each of these and add them all together and then subtract from 500. That's probably the most intuitive way to do it. So let's do that. It's a little bit more tedious, right? But it would be 500 minus whatever the sum is. All right. 90 and 110 is 200. 200 plus this 100 is 300. 300 plus 150, because this is 80 and 70, is 450. And 450 plus 10 is 460. So this would be 500 minus 460. You can add them up in any order you feel comfortable, right? 500 minus 460 would be 40 outside all of them. All right. Now that you have a completed diagram, you can answer any other specific question about them. All right. But the exercise is really what is important, how to fill in the diagram. All right. There's a logic to it. Now, using the completed three-set Venn diagram from above, how many people do not listen to country music? Now, I just kind of shot myself in the foot, didn't I? Because I erased everything. How many people do not listen to country music? Well, if I fill this in, I can look at it and make that determination. What is not country music would be everything outside the overlapping green circles. So if I just shade all of this as if I were deleting it out, in this instance, the context in which I'm using it here. Look outside the crosshash, right? People who are not country, if you will, C prime, would be the sum of 40, 100, 90, and 110 in theory, right? So that's 200, 300, 340, it should be. Okay. Now if you look at the next thing, this is a list of the rules of divisibility as they could be applied to a number 963,888. Remember, most things are dividable, the exception being 0, 0. Can't divide by 0. But fewer things are actually divisible, all right? By specific numbers, which means that you will not necessarily get a remainder of 0. If things are truly divisible, the remainder would in fact be 0. You could say it doesn't have a remainder. You wouldn't bother considering it. This is a summary of rules of divisibility. This is, not to corrupt you, but this is more or less the way that I go about it myself mentally when I'm checking a number. All right? And if something is even, all right, then it is in fact divisible by 2, which means remainder 0, or you could say no remainder. Now, if you have the number 963,888, is this an even number? If it were, it ends in a 0, 2, 4, 6, or 8, and it does. So you would say, yes, it's divisible by 2, meaning it more or less divides nicely. A little more involved is the rule of divisibility for 3. You can divide a number by 3 nicely. That is no remainder, or you could say remainder of 0, if the sum of the digits happens to work also. So if you took this number, 963,888, and you added all the digits, what would you get? All right. 9 and 6 is 15, 15 and 3 is 18, 18 and 8 is 26, 26 and 8 is 34, 34 and 8 would be 42. So this ends up being a sum of 42. Now, if you want, you could actually apply the rule again, which is to add these two, and then you get 6. All right. Can you divide 6 by 3 nicely? That is, that you don't get a remainder. The answer to that is also yes. All right. 6 divided by 3 is just a number 2. All right. Then there's the rule for 6, which says that if a number is divisible by both 2 and 3, then 6 is a better choice, perhaps. And they are, because we just verified that, so yep, continuing. The sum rule is also something that you could apply for 9. So I wouldn't go as far as adding 4 and 2 in this case. If you're just stuck with 42, all right. Can you divide 42 by 9? You could certainly divide it, but it's not divisible by 9. What would happen if you divided 42 by 9 is that you would definitely get a remainder, right? 9 goes into 42 roughly how many times? Let's see, 4 times, which would be 36, and the difference would be remainder 6, right? So it's not divisible by 9 per se, so you would say no. In that case. The rule for 5 and 10 is very similar as well. 5 has a little bit more leeway. Does it end in a 0? 9, 6, 3, 8, 8, 8. 9, 6, 3, 8, 8, 8. Absolutely not. It ends in an 8. So you would say no. Right? Won't divide nicely by 10. Does it end in perhaps a 5? No. So it's not going to work with 5 either. All right. Then there's the rule for 4 and for 8, which are very similar, except that 8 is a little bit, you have to look at more digits. All right. If the last 2 digits divide nicely by 4, then the whole thing will. So if you see, as in this case, 9, 6, 3, 8, 8, 8, and you're just paying attention to the 88 portion of this, can you divide 88 by 4 nicely? Yes, it would just get 22, right? So yeah, it will work with 4, all right? What about if you looked at all 3 digits? Well, the last 3. Can you divide 888 by 8 nicely? Absolutely, you get 111. Right. There is, I've heard of a rule of 7, but to me it's much more complicated than it's worth, if it in fact is legitimate. The best thing to do in the case of 7 is to divide by 7 and see whether you get a remainder or not. So it's annoying, right? But if you took 963,888 and you divide it by 7, we'll see if we get a remainder or not. Do short division, because I really didn't give you a lot of space here, unfortunately. I'm doing this, 963,888 divided by 7 nicely. 7 goes into 9 one time with 2 left over. 7 goes into 26. I may need a little bit more light. That's a little bit better, maybe. 7 goes into 26 3 times, which is a difference of 5. 7 goes into 53 7 times, which is a difference of 4. 7 goes into 48 roughly 6 times. That would be 42. Difference of 8 would be 6 again. 7 goes into 68 9 times, which would be 63. The difference would be 5. And 7 goes into 58 8 times with a difference of 2. So this would be remainder 2. Alright, and therefore, since it's a remainder of 2, you would say no, it doesn't divide nicely. It's not, i.e., it's not divisible. Okay, so in summary, what are the numbers that this 963,888 would be divisible by? 2, 3, 6, 4, and 8, and you could put them in numerical order. Okay. Moving on, prime factorization. determine the prime factorization of 222. You can use either factor trees, which is maybe something more intuitive, maybe a little bit more conducive to a kid because it's a tree diagram. Or try this other technique, I don't know how else to call it, but by the way it looks. Upside down division by primes. Right? That means that you have to understand divisibility and you need to recognize prime numbers simultaneously. I'll do it both ways. All right, if you did it this way first, it's upside down division, at least from the perspective of an American that lives on the East Coast. All right, so that box is like that. All right, what is the lowest prime number? Well, here's some primes. All right, the lowest prime number is 2. All right, is it divisible by an even number like so? It is. Therefore, you use it. All right. And you keep using it until, that is, you keep dividing by 2 until you've exhausted it. It can't work anymore. All right, so 2 goes into itself once, and 0. Still even, so you can still divide by 2. 2 goes into 11 roughly 5 times with 1 left over. 2 goes into 10 exactly 5 times. All right, now, the temptation might be to jump the gun and immediately go for 5. It's going to be 5, to be honest, but you should check them in numerical order. So check 3. In other words, is this divisible by 3? If it were, then you would in fact do that. All right? It's not, because it would end up being 10. 5 plus 5 is 10. That doesn't divide nicely by 3. So you're going to skip 3 now after having verified that, and indeed use 5 because it ends in a 5. 5 goes into itself once, right? And that you stop when you've hit a prime number, which happens to be 11. This is the prime factorization in this jelly bean, right? If you did it with factor tree, it's a little less strategic, right? It's just whatever intuitively occurs to you, right? And you keep breaking it down to branches until you've struck mathematical gold, right? That is, it's all prime numbers at the bottom, right? You might intuitively go, well, this ends in a 0, so it would be 10 times something, right? What would it be 10 times? Well, 22. Neither of which is prime, so I would have to continue. If I factored down 10, it would be 5 times 2, both of which are prime. If I factored down 22, it would be 2 times 11, both of which are prime. And you get the same prime factorization, it's just, botchakaloop, it's done in the same order. If you want now, what you could do is use abbreviations, which would be good and not for other reasons, to sort of abbreviate exponents. So 11 to the first times 5 to the first times 2 to the second would be the fancy way to write it. All right, now what's the purpose of that? The prime factorizations are useful when you're looking for either greatest common factor or least common multiple. How you apply them is different depending upon which you're looking for. So here's 25 and 35. In the case of the greatest common factor, were you going to use the prime factorization to determine this? What you want to do is to use the lowest power of each match. I know it's called greatest common factor, and that may seem a little ironic that you're looking for a low number, but that's how it works. All right? In the case of least common multiple, what you want to do is to use, again, somewhat ironically, the highest power of each unique prime factor. Okay? You don't care about matches when you're concerned with least common multiple. Now, what are the prime factorizations of 25 and 35? They're pretty easy, right? Here's 25, right? It's just 5 times 5, which is 5 squared. And here's 35, it's 5 times 7, which is 7 to the first and 5 to the first. Using the exponents for the sake of abbreviations helps you get through this and this. That's the point. Now, if we're looking for the GCF of these two figures, 25 and 35 respectively, again, use the lowest prime, the lowest power of each match. Now, the only thing that matches in the case of 25 and 35 are 5. So you want the lower one. What's the GCF? It's 5. When you're looking for LCM, you want the highest power of each unique thing. What is the thing? Each unique prime factor. These are factorizations, right? We don't care if they match, we just sort of want to cover everything. So, of the 7s, there's only one example, so we must include that. Of the 5, we want the higher one, which would be 5 squared. Okay? Now, we want to get a satisfying number, so we're going to do the actual multiplication in this case. It's really 7 times 25, which is 175. And you might say to yourself, well, that's kind of annoying. Why do I got to do it that way? I would advise you to do it this way because, especially if you had 3 numbers to do simultaneously and not 2, you could see that it might be a while. If you listed multiples of 25 and 35, it might get a little cumbersome. Like here's the multiples of 25, which I could recognize easily just because of, handling money. 25 cents, 50 cents, 75 cents, right? 100, 125, 150, 175. When you're doing something that is less familiar though, like the multiples of 35, it can get a little more intimidating. First multiple of 35 is 35, naturally. The second one would be 70, then 105. Then that much added would be 140, and then 175. It might be a while before you get to the least common multiple. It's trickier to have to list those. Least factors are, finite. Multiples are not finite. All right, now, this thing that you see in the blurb here is the circle. It's just to remind you, right? It's not really the actual question. The question is 13. All right. In the case of adding or subtracting integers, you know that there's a set of rules that are understood as being different than when you multiply or divide integers. All right. What are integers? Negatives, positives, or 0. That is, negative or positive whole numbers, no fractions technically, are called integers. Or decimals. Right. In the case of adding and subtracting, it is the combination of signs ultimately that determines the operation. So what you see is not necessarily what you get or what you do. The sign of the answer is always the same as that of the larger magnitude. Magnitude is the distance from 0. Right? If you're given a double negative between numbers, you can change it to a positive first. Now look at this problem here. Right? For 13, you see kind of the worst case scenario in terms of signs. The question is actually not the sum of the difference. It's just following this train of thought, which operation would you actually do? All right, depending upon this combination of signs that you see here. Well, what you have is a double negative between the numbers. So I know that there's a parentheses here, but that's just because it's not written in superscripts. When you have a double negative, what does that enable you? To write this as a positive instead. All right? Now, if you look at this as -4 and +3, the rules for signs, adding, subtracting rules are, if they're the same, you actually add. If you have one of each, then you actually subtract, which is what you have in this case. You have -4 ultimately, and you have +3 ultimately. So, what is the actual value? It's going to subtract to produce a numeral of 1, and then the sign of the answer is always the same as that of the larger magnitude. That is the thing with the greater distance from 0, which would be 4, and that's a negative. So this is -1 if you're curious. All right, now the answer to the question is you're going to subtract. All right, that's really more important, being able to know what to do, because of course you could just get your calculator, to verify for you, right? It's a little tedious, but here, right? -4 minus -3, right? Notice there's no parentheses here because it's not really imperative. What do you get? -1, right? But how did it produce that, right? It is the combination of the signs ultimately that determines the operation when you're adding or subtracting potentially. All right. Now, the other set of rules is for multiplication and division. Okay. In the case of multiplication and division, the combination of signs does not determine the operation. If you multiply, you multiply. If you divide, you divide. The only exception would be maybe if you had some kind of fractions involved. But that's for a different reason, right? Instead, the sign of the answer is decided by the sign combination. So the outcome, more or less, is going to be positive or negative depending upon whether they're the same signs or they have one of each. All right, again, following this train of thought, what will be the sign of the product? This is a multiplication problem. All right, notice what I did. You know, like for problem 13, I gave you these figures. All right. Versus for problem 14, I gave you the exact same things, but a little bit more concisely writ. Right? This is ultimately an addition/subtraction problem, right? Why? Because it becomes +3 and -4. Right? There is a sign in between the numbers. Right? This, although there is a parentheses and it's very similar looking, is a multiplication problem. Right? Because this is just an alternative way of writing multiplication. Instead of saying 4 times -3, or -4 times -3, or -4 times -3, or you can put them both in parentheses as independently of one another. These are different ways of saying multiply. Right? So, you do the multiplication because you recognize that's the operation. It is in fact 12, right? But what is the sign if they have both negative? Same signs as a positive. So this is +12. Okay? Make that distinction. It's very important. A lot of times people, because they're so dependent upon the calculator, unfortunately, it's a nice convenience to have it. They absolve themselves of memorizing stuff, and that's detrimental for more sophisticated problems. All right, so make sure that that's down pat, and that when you're teaching, you impress upon your students the importance of that. Alright, now you're going to convert a mixed number to an improper fraction. It's a bit tiny, and I'm sorry about the way that this is written. How it would be written nicely would be like that. Alright, remember, this is a procedure. You multiply these two things, and then you add that to the top. Right? So to convert this from a mixed number, that is a whole number in the front, a fraction attached to it. 2 times 5 is 10, plus 3 is the new numerator of 13. And then you keep the same denominator, so it's 13 fifths. Fifths. Okay. Okay. Now, what if you have to convert a repeating decimal to a fraction? If you're curious, let me just do this really quickly because I'm tempted. If you had to convert an improper fraction back to a mixed number, it's dividing, really. You just draw the box, plop this in here, and if you get a remainder, you make that a numerator. So how many 5s can you squeeze into 13? Roughly 2, which is 10, and the difference is 3. That's your remainder. And then what you divide it by is your denominator stuff, 2 and 3 fifths. All right. This problem of 0.6666 repeating, El Diablo, this involves a little bit of algebra as a strategy. All right. The strategy of algebra is to call a number by a letter. So let's just start with n because it's intuitive, right? and then I'm going to write this pattern here. Right? N is going to represent 0.6666 repeating ellipses to indicate infinity. Okay? Now, when we do this, we want to preserve some portion of the pattern while also deleting off anything that is not necessary. You preserve a portion of this by scooting what repeats over to the point where the decimal is just past it. So what would it take to do that, though? That's the same as multiplying by what? Multiplying by 10 ultimately accomplishes this, which makes 6.666 repeating. Now if you do the actual subtraction, this is really a stand-in for 1n, 0.666 repeating. And you subtract both sides independently. So this, you get the satisfaction of doing 10 minus 1, and that gives you 9n. And this gives you the satisfaction of just being 6. Why? Because infinity gets erased strategically. Right? We've aligned them, and when you add or subtract decimals, remember the place values have to align. And we have purposely rigged the machine so that infinity gets deleted off. So you have 9n equals 6. Now you employ the actual game of algebra, which is to perform opposite operations. Why? Because we're dragging this 9 from over here to there. Whenever you go over an equals to solve for the letter, in this case you have to, you do perform the opposite operation. If two things are pressed together, it is implied that they're being multiplied. So the opposite of multiplying would be dividing by 9, which we favor writing in this style in algebra. If you divide by 9 here, for the sake of balancing, you do it here as well. The 9's cancel, leaves you with 1, which you don't have to write. And then n is therefore the simplified form of 6/9. Right? 6/9 is really divide by 3 each. You get 2/3 rather. So 0.666 forever and ever and ever is 2/3. Or 6/9 if you didn't simplify it. Okay. Now, 17 is an order of operations problem, so you have to do potentially, all operations, but you do it in a particular order. So what you have here, if you write it out nicely, is that this is 13/15 minus 14/45 divided by 7/9. Okay. You only have two operations, but where should your focus really be? The order of operations dictates that your focus would be here, right? Because division is of higher order than subtraction. When you divide fractions, remember that you end up multiplying, but you have to apply this principle. Keep, change, flip, which is to keep the first fraction exactly as you see it, 14/45. You change the operation, perhaps somewhat ironically, to a multiplication. We'll use the dot in this case. And then you flip this 7/9 over to a reciprocal of 9/7. 9/7. Right? Now you could at this point just do brute force, top times top, bottom times bottom, and simplify it as an afterthought. But the more strategic thing would be try to simplify before you multiply. It just so happens that the numbers work out rather nicely in this case because there's a relationship between all of them. If a person memorizes their multiplication tables, and they really ought to, they would recognize that there's relationships between things above the line and things below the line, whether they're diagonal more or less or directly above and below. 9 and 45 you might recognize from the multiplication tables of either 9 or 5. They're both made of the number 9. So you can simplify. 9 divided by 9 to simplify would be 1 left over, and 45 divided by 9 would be simply 5. At the same time, there's a relationship between this 14 here and this 7 here. Again, as long as one is above and one is below, it doesn't matter if they're directly above or below or diagonal. You might recognize these from the 7 times table. So you can simplify them therefore by 7. All right, 7 divided by 7 is 1, and 14 divided by 7 is 2. All right. Now you do left over top times left over top, and you would get a 2 on top. And left over bottom times left over bottom, and you would get a 5. And 2/5 is a lot easier to deal with, all right, than the original thing. Now, I'm a little short on space, so what I'm going to do is I'm going to erase this gobbledygook here and just replace it with that. This reduces to 13 over 15, 13 fifteenths minus 2 fifteenths, 2/5. And now you have the issue of, well, they don't have the same denominators. Remember, when you add or subtract fractions, the denominators must match. So what you do is you upgrade to a common denominator. You could just pull the trick of multiplying 15 times 5 and using 75 as the common denominator, but the ideal situation would be that you use the lowest common denominator. That is the LCM, least common multiple, of 15 and 5, which would actually be 15 itself if you counted out the multiples or used prime factorizations. Now be consistent. All right, 5 times what would be 15? 3. And if in theory it takes that to get from here to here, you're obligated, you have to do the same thing consistently to the top. 2 times 3 would be 6. All right. Once you have a match, you really just need to pay attention to the things above the line. It's 13 minus 6, which means that it's 7/15. And it ends up being a positive for that reason. Now we apply some rules of exponents here. Use the power rule. In this case. The power rule is when you have an exponent raised to an exponent. And in that case, you just have to multiply these. And you would end up with 2 to the 20th, because 4 times 5 is 20. Now, it would be more practical in this case to leave it simply in exponential form rather than in the standard number, because the standard number is quite vast. All right, it ends up being this, right? 1,048,576. Right? That's illustrating the point of exponents as being an abbreviation for large quantity. Okay. Now, taking that to the nth degree, pun intended, if you convert a standard number, regular number, to scientific notation, that looks something like this. You would have a decimal times some power of 10, right? And it has to be one non-zero in the front. Otherwise, it is not technically scientific notation, even if it has the times 10 next to it. Okay, here is the mass of an electron. Right. The way that I've taught it is that we reserve direction and sign for when you're converting from the standard number to the rather, when you're converting from scientific notation to a standard number, all right? Just think about it this way when you're going the other direction. When you take something and you write it in scientific notation, just identify it as either being a very small number or a very large number. Large things have a positive power of 10, and very small things, even less than just 1, like 1/10, all right, would be a negative integers, negative power of 10. Negative exponent. So just count the number of leaps from here to here. All right, here's the decimal where it starts. You can count by 3s. This is the way we write it in the United States. No commas here and no decimal points. We just group things in sets of 3, and we're supposed to leave an obvious space. So you can count by 3s. 3, 6, 9, 12, 15, 18, 21, 24, 27, 30. And then because we have to meet the requirement of a non-zero in the front, we go 1 extra space, and that makes us 9.11. times 10 to, what's the total number of leaps from here to here? 31. Because this is a very puny thing, right, it's a negative exponent. It doesn't make the value of it negative. It just, interestingly, is talking about an electron. All right, it's the exponent direction is negative. Okay. Similarly, although we're going from the other direction, when you convert from scientific notation to a regular number, now reserve sign and direction. Right? If you're taking something that is a positive exponent, and this is a positive 8, if it's not written, you assume it is. Positive means move the decimal toward the right. So you have this 1.5, and you're going to make 8 waves that way to the right. 1, 2, 3, 4, 5, 6, 7, 8. And in the void, you fill in zeros. And if you live in the United States, 1, 2, 3, 4, 5, 6, 7, 8. You put a comma after every 3. So, comma here, comma there, which means that this is 150 million kilograms. Kilometers, rather, it's km, sorry. Distance is not measured in kilograms, that's terrible. Mass is measured in kilograms, distance is kilometers. Okay? And that's it. All right. So again, you don't have to submit this. I'm going to give you credit for it. What I'm really more concerned with is that you finish your MyLab assignments, which are related. There is an extra credit assignment when I was teaching in person, so I'll show you that just for the sake of it. What to do if you have mixed numbers. This doesn't really come up much in your work, but as a teacher, you might see it. When you're dealing with a negative or a positive, in this case, this is a regular problem, so you don't really have to worry about it. The strategy is to convert mixed numbers to improper fractions, right? When you see involved, when you have a negative somewhere involved, that's probably the best course of action. Convert your mixed numbers to improper fractions, but this is a normal one where you have a larger number on the left side of this, so I'll just walk you through it the traditional way first, and then I'll do it this way second. It's actually more cumbersome doing it that way, but it's good to have the mental flexibility. If you have 69 1/8 minus 67 3/8, right? We don't have the issue of them having different denominators, so we don't have to find a common multiple or common denominator first. What we have is we're subtracting fractions and we're subtracting whole numbers. The larger quantity overall is on top here, so we don't have to worry about integer issues, sign issues. But we would have to consider 1 minus 3, and that means that we have to borrow in a case like this. So you would borrow the amount of 1 from the whole number. That would reduce this to 68. And then rather than simply add 1 to the fraction, you write 1 in the style that is convenient. So if it's an 8, you make it 8/8. 1 whole is 8/8, right? Just like 1 whole would be 7/7, so 6 6s and so forth. All right. Now 1 and 8 is 9/8. And now this is appropriately good to go for subtracting. All right. What is 9 minus 3? 6/8. All right. What's 68 minus 67? 1. So if you bring it all together and you write it in simplest form, it would be 1 and divide each of these by 2 to simplify. That would be 3/4. 1 3/4. Right? That's the answer regardless. Now if you do it in the newfangled way, which is to make these improper fractions first, and again I would reserve that for the issue when you have a sign in here. All right. What you would do is you would take your 69 1/8 and convert it to an improper fraction first. So it's a little cumbersome. 69 times 8 9 times 8 is 72, carry the 7. 6 times 8 is 48. 48 plus 7 would be 50 what? 55, right? And then 55 plus this additional 1, 552. Plus 1 would be 553 over the same denominator of 8. So it's kind of a crummy number, but it works. Right. Now the other figure, 67 and 3/8, same thing, right? You have to multiply these two first and then add them to the top. So if you had 67 times 8, that's 56, carry the 5. 6 times 8 again is 48. 48 plus 5 is 53. So you have 536 to begin with, plus the 3 that is there, and that leaves you with 539 over 8. Okay. Why go through all this trouble? Because if an integer was involved, borrowing would get you into some deep trouble. All right? It would definitely be a recipe for disaster. So now that you have these over a common denominator and you have everything squared away in terms of their improper fraction numerators, you can do the actual subtraction. Right? What is the difference between 553 and 539? 1, 10, and then another 3 is 14. This would be a difference of 14 over 8. Now, if you had this originally in mixed numbers, you give it back, right? This is an improper fraction, 14 over 8. You could reduce it first if you want. Divide by 2, divide by 2. That would reduce this to 7 over 4. 4 goes into 7 one time with 3 left over. You'd still get 1 3/4. Right, either way. It's good to just have the, be aware of the options that you have. Okay? So let me turn this off and I'll tell you what we're doing. And that will be it for today. Alright, for homework, remember you want to finish your MyLab assignments to this point. This is everything from section 2.1 through 5.6 with the exception of 4.4 and 5.5. That's going to be new stuff next week. You're not going to get in that yet. And the prerequisites as well. Right, this is all due tomorrow night. Okay. Again, you don't have to submit the test. I made it more or less for you to have a gauge of what you should know at this point. Right. I want you to focus on completing your MyLab assignments. All right. When it comes to the final exam, your exam is going to be most likely in MyLab. And that's another assignment at the very end, right? But my own stuff that I make, I don't mind giving to you as a freebie, okay? So thank you guys for sticking with me. I will see you again on Wednesday. Be careful out there.